Okay, geometric examples. Hopefully you're okay with that. Sorry, I was about to run out of battery at the end of my last clip. So the nth term is AR to the power n minus 1. So that's all we're working with at the moment. So for this geometric sequence here, we know that the first term is 5. To find the common ratio, we're timesing by r to get to the next term. And so 5r is equal to 16. And so r is equal to 16 over 5, which is 3.2. You could equally do 16r equals 51.2. And then if you want, for instance, the 8th term, so notation for that, use subscript 8, will be a times r to the power of 7, which gives you 171. If you want the nth term, so nth term, then that would be 5 times 3.2 to the power of n minus 1. So that's what a term looks like in a geometric sequence. So that's the first one. Second one, I've deliberately made the numbers awkward actually in these so that you can't just see the answer. Right, we have the second term is 27 and the 7th term is this. So second term equals 27. So similar to before with the arithmetic ones, you need to think about setting up simultaneous equations. So the second term, AR to the power n minus 1, so AR equals 27, and the 7th term is negative 8.84736, and so AR to the power of n minus 1 is equal to that. I think the numbers got slightly too awkward, but never mind. So we have two simultaneous equations in A and R. The easiest way to do this actually is to do, you can do equation 2 divided by equation 1 if you want to, or you can rearrange and substitute in, but that's the easiest way. So AR to the power 6 divided by AR is going to give you R to the power 5, and that is equal to, sorry, lost my thing there. So it's negative 8.84736 over 27, which is negative 0.32768. And if you take the 5th root of that, you get R is negative 0.8. And if you put negative 0.8 into here, you get A is negative 33.75. So similar to the arithmetic ones, set them up, solve two simultaneous equations. Third example, I'll let you pause these if you need to. We want to find the first term to exceed 2 million in this one. So the first term is 0.5. I'm timesing by 4 to get to the next term, so R is equal to 4. And if you think about the nth term equaling 2 million, you could do bigger than 2 million, but you'll have to think about whether you need to flip your sign or not. So this way is fine for these. And so if the nth term equals 2 million, then the next one along will be bigger than 2 million because the sequence is increasing. So you need to think about, is it increasing, is it decreasing, and stuff like that as well. Nth term is AR to the power n minus 1. So 0.5 times 4 to the power of n minus 1 equals 2 million. And we now have an equation with an unknown as a power, so you can use logs to solve it. First of all, I need to divide both sides by 0.5 because you just need the expression with a power on its own first, really. Then I can take logs of both sides. You could take natural logs, logs to the base 10, so whatever base you want to, this will work. So if I take base 10 logs of both sides, then I can pull down the power. And then n-1. Actually, let me scoot that over to there, so I've got room. So then n-1 is equal to log of 4 million, which sounds horrendous, but it's not really because we're dealing with powers, over log 4. Put that into your calculator and you get 10.97. And so n from here is equal to 11.97, and so n is equal to 12. Remember, n is taking positive integer values because it's the number of terms. So the first term to exceed 2 million will be the 12th term. The last term to be less than 2 million will be the 11th term. So you can use your common sense from there. And then, last but not least, we have first 3 terms. Just checking the time. No, we're fine for time. The first 3 terms of a geometric sequence with positive terms are 3x and x plus 6, and we want to find x to start with. So the only thing we really know is it's geometric. So we're multiplying by r to get to the next term. And so 3r equals x, and xr is equal to x plus 6. And so from this one here, r is equal to x over 3. And this one here gives that r is equal to x plus 6 over x. So it's that same idea. If you divide one of the terms by the previous one in a geometric sequence, you'll always get r. It's worth kind of remembering that. So this gives... So if r is x over 3 and x plus 6 over x, then x over 3 must equal x plus 6 over x. So I can times right through by x and times right through by 3. So that will give me x squared equals 3x plus 18. Sorry, I haven't got the best amount of space here. We've then got a quadratic in x. So it's going to be x minus 6, x plus 3. And so x equals minus 3, or x equals 6. If we go back to the question, it says the geometric sequence has positive terms. I should probably put an all in there with all positive terms. And so in that case, that's not going to work. And so x must equal 6. It's possible you could have 2 solutions though. This will give you alternating positive, negative terms. I think, yeah, it will. In fact, it will just go 3, minus 3, 3, minus 3, 3, minus 3 if you look at it. So to find the 10th term here, we now have a is equal to 3. If x is 6, then r is equal to 2. So r is equal to 6 over 3, which is 2. And so the 10th term is equal to AR to the power 9, which I'm going to have to put into a calculator. We've got one. So 3 times 2 to the power 9 gives me 1536. And then to find whether 12210, 12,210 is in the sequence, if it is, then it needs to be a term in the sequence. So for this particular sequence, the nth term is equal to AR to the power n minus 1. And so substituting this into the left-hand side, we get 3 times 2 to the power n minus 1, dividing by 3, sorry, get 4070. And then if you take, you don't need to take logs of both sides, you could just actually do that n minus 1 will equal log to the base 2 of 4070. Or you can take logs of both sides, bring down the power and divide, either or. And log to the base 2 of 4070 gives you 11.99, and when you add 1, n is equal to 12.991. I meant this to be not quite as integery as this, but this is not in a sequence because n is not an integer. I should have made it slightly smaller to make it clearer, probably. So it wouldn't need to be an integer exactly unless you've rounded somewhere. If you compare that with 12288, which I could just pop up there in a different colour. So if you do 12288 and you do 3 times 2 to the power m minus 1 equals 12288, and then divide by 3, which gives you 4096, and then you can rewrite that power as a log, or take logs of both sides like I did in the other example, either or. And if you put that into a calculator, you should find you get an integer. So log to the base 2, I'll just put 3 in, 2 of 4096 is equal to 12. Add 1 and you get 13 exactly, and so this will be in the sequence. So there's a couple of questions involving that in the exercise. So because n is an integer, that one is in the sequence. So 2 ways of solving your logs. You can either rewrite them as a power, or you can take logs of both sides. If you're working with inequalities here, I would go with taking logs of both sides, but we'll worry about that a little bit later. So either or.